Indiana University East School of Natural Sciences and Mathematics. Introduction to Acids and Bases. So, as you may know from everyday life, there are a range of different substances that are acids and there are ranges of different substances that are bases. Many of our foods, most notably citrus fruits, are acids. In turn, many products, most notably quite a few cleaning agents, are bases. In this course, we are mostly interested in defining what a base and an acid are to get a good definition of them, and then we're going to find ways of classifying them, and finally we are going to look at neutralization reactions. So the Arrhenius definition of acids and bases is the first one. Okay, we need to first recognize that acids are molecular, and therefore they only ionize in water in this case. So the Arrhenius definition of acids is that they lead to an increase in protons. H plus ions will be increased. Now, in reality, H plus ions are highly reactive, so they don't actually exist in reality. So what actually exists is that it actually combines with water to form at minimum the hydronium ion. Now this is the description that is used in general chemistry. In more advanced chemistry courses, it gets a bit more complicated than this. But we're going to leave it alone. And in this course and in C106, we will deal with the hydronium ion. In turn, bases in Arrhenius definition increases the concentration of OH minus ions. Okay. The problem with this definition is that it really only works in water. It doesn't work for all acids and bases. You have to realize that there are three different sets of definitions, and each they get more and more general. So the Arrhenius is the most specific one. Now, a more general definition is the Bronsted-Lowry theory, which is what we're going to use. So, as a general point, Arrhenius acids and bases form a subset of Bronsted-Lowry acids and bases, and therefore a Bronsted-Lowry base need not be an Arrhenius base, but an Arrhenius base is always a Bronsted-Lowry base. So what's going on here? Here we define an acid as a proton donor while a base is a proton acceptor. And in any acid-base reaction, you must have both an acid and a base reacting together. You can't react an acid by itself and call it an acid-base reaction. An example of such a case is when I dissolve HCl, hydrochloric acid, in water. As we saw before, and this is a strong acid, so it ionizes completely. It would form the H plus. So this is going to ionize, so you have H plus and Cl minus, and the H plus actually joins with H2O to form H3O plus, the hydronium ion, and you're left with a chloride ion. Okay, so if I look at this case, I have HCl as my acid, and it loses the H plus here. In turn, here water acts as a base, and it gains an H plus. One thing to note is that in quite a few calculations we use H plus and H3O plus interchangeably. If I want to write a net ion equation for this, it is going to be somewhat less instructive, but essentially you have your H plus, because this is a strong electrolyte, it's considered to be separated out. Another example to consider is ammonia in water. Now, ammonia is a weak base, so it only acts as a base very slightly. It's in equilibrium. So we draw these arrows here, and we form the ammonium ion, NH4 plus, and we get OH minus. I'll explain what this double-headed arrow equilibrium sign means later. So this is a base, but here we can see that the base, when it reacts, gains an H plus. So you see we have one more H, and we gain a plus charge. While here, water acts as an acid, and therefore it loses an H plus. This is typical of base. Now, we will look into this sort of thing a lot more carefully when we go into chemical equilibrium and acid-base equilibria when we get into C106.